maybe while they're setting up their screen, I'll just take a moment to introduce them. So we have our next speakers are Kelly Goedert and Susan Nolan from Seton Hall University.
And we pre-recorded our talk, so Kelly's going to play it, and we're here in the chat and also to answer questions at the end.
Okay, thank you.
So hopefully this works.
Hi, everyone. I'm Susan Nolan, and I'm going to be presenting today with my colleague, Kelly Goedert. We're from Seton Hall University, which is in New Jersey in the US. We are excited to be here today and are grateful to Kevin Peters for organizing this wonderful two-day conference on the teaching of stats. It's really exciting to have a conference dedicated solely to the teaching of statistics, and we're really happy to be a part of it. I'm going to talk first about weird samples, and then Kelly is going to talk about small samples, and we'll give you an activity for each that you can use in your statistics, research methods, or related classes. So first, the problem of weird samples. As you likely know, weird samples are those that are Western, educated, industrialized, rich, and democratic, or I should say from countries that are overwhelmingly Western educated, industrialized, rich, and democratic. These tend to disproportionately be English-speaking countries, such as the US, Canada, Australia, and the UK, but we also have a number of other Western European countries who are disproportionately overrepresented. So we've seen a lot of headlines in recent years like this one. You can't characterize human nature with studies that overlook 85% of people on Earth. There's been a lot of research that's actually looked at our journals. In this study of all articles published in Psychological Science in 2017, 93% of studies were from the countries in blue, which only represented 12% of the world population. These, as you can see again, US, Canada, UK, and Australia and New Zealand as overwhelmingly the English-speaking countries, whereas in Western Europe as well, whereas the rest of the world is very much underrepresented. This is an article by Arnett from 2008, which looked at more journals, and found similar patterns. This shows the percentage of US first authors on papers in all of these major journals. The follow-up were authors from English-speaking countries, followed by Western European countries. Israel was pretty high in there as well as an addition. For second authors and other authors as well, the same pattern emerged, as it did for editors. So these researchers, even though it's not directly looking at samples, the researchers overwhelmingly were writing about samples from their own countries. In addition to the problem of weird samples, there's also a problem of an assumption of universality, which is particularly pronounced in the United States. So this is the idea that if we conduct a study here, well, then it's going to just map onto everyone everywhere. This is a problem in other weird countries too, but it's particularly prevalent in the United States. So one study by Chion et al. In 2020 found that US researchers were far less likely than their counterparts in other countries to provide the name of the country, the US, where they did their research, right in the title and right in the abstract, so you can know upfront. So Chion et al. Quote from their study, I'll let you read it. So fascinating that only if there were minoritized groups in the study were the samples represented up front in the title and in the abstract. So in my classes, I've had an activity where students have to choose a journal and find the latest issue. And I particularly push them to find one that has at least some international articles in it, because otherwise it sort of doesn't really make the point that I'm trying to make. So we fish around. I'll approve it once they find it, and then they'll go ahead and they identify the countries of origin of all of the researchers listed as authors, of the journal's editors, which they might then have to go look up, and of the sample. Then they looked as to whether the sample country or anything about the sample in terms of demographics is listed in the title or the abstract. And finally, they look as to whether or not the researchers made any statements about generalizability, either informal or as a formal statement. The informal might just simply be in the discussion where they talk about constraints on generality, or it could be an actual COG statement, a constraints on generality statement. There aren't a lot of those right now, but they're starting to be more popular, which I think is a really wonderful trend. Even if my students don't end up finding COG statements in the journals that they choose, I show them representative samples of COG statements as well. We then compile data from across the class. We do some stats on it, just basic, crosstabs, little chi-square graphs, and then we discuss the patterns that we see, which usually fit the patterns that I showed you from earlier research. Just as an example, this is from a relatively recent issue of Sex Roles, a journal of research. You see there's one at the top, which doesn't mention anything about the demographics in terms of country or racial or ethnic background, and then the one below where it talks about the fact that it was in China, it was Chinese female college students. Any guesses as to where the top one was from? Yes, the US. We again do see this in other weird countries, but not to the same degree. For example, from the same issue, we have a study that looks at college students in Canada, where the country is specified. As I noted, I also talk about this idea of COG statements and the importance of them, and I've been encouraging my students in their own work to include a COG statement in their paper to pay attention to the limits on generalizability. And in fact, COG statements, although great, aren't always perfect. So this is an article that I actually have also used in some of my classes, the fact that trigger warnings are not necessarily helpful. And the COG statement for that article, and again, I'll let you look it over. So as you can see, it talks about whether or not this would apply to other situations, different lengths of time, etc. But where's the weird? There's no mention here about their sample or how far it might generalize to other samples or other countries. And now I will turn you over to Kelly. Thank you.
So thanks, Susan. So I'm going to walk us through an example of an activity that we can use to teach statistics or research methods students about the problem with small samples or underpowered studies. So when I grew up doing statistics, and I do feel like I grew up doing statistics, the prevailing logic was essentially this. Assuming null hypothesis significance testing, if the null hypothesis is false, then the larger our sample size, the lower our p-value should be. And there was this assumption that essentially this is kind of a linear type function. And so if we were doing a study and we had a sample size, say, of 10 to 12 people per cell in our experiment, we might feel like, meh, that's not that great a sample size. But then we would double that sample size and we would have 20 to 24 people in each cell of the experiment and feel like that was just fantastic. And thinking all the while that as we increase our sample size, we're going to decrease our p. So as long as the null hypothesis is false, as we increase the sample size, we're only going to be able to better detect like the truth. Well, as it turns out, this isn't quite the case. So essentially what I was just describing is an assumption that there's a linear decrease in p-values as our sample size increases. And with the advent of computer simulations, we can now very much test whether this is indeed the case. And so this was a publication by Simmons and colleagues in 2011, when what we're looking at here is the results of a computer simulation that they did with an effect size of 0. And they were doing an independent samples t-test comparing two conditions. And on the x-axis, we see the sample size in each of the two conditions. And on the y-axis, they have the p-value that resulted from that particular sample. And so in each case, right, they started with observations of 10 in each condition, and they just added one person at a time to each of the 2 cells. The red horizontal line here is our magical p-value of 0.05. And what you can see is that initially the p-values for this study are relatively high in the 0.3 area, and they actually dip down to less than 0.05 for some of the tests involving, looks like between 23 and 27 participants per cell, before going back up. But the big take home here is that this assumption that there's a linear decrease in P as N increases is completely unfounded. So the activity that I've piloted with my laboratory group is using G-Power, it's freely available software, in order to get students to actually run the power analyses for published studies and to have them look at both post hoc power and a priori power. Now, it would be super nice if we could do something like what Susan did and have people go through every journal article in a particular issue of a journal and assess that. The problem is, and as you, I'm sure understand, that the statistics presented in the journal articles are much more complicated than typically what the students are used to seeing. And so what's really required is that ahead of time, you go and you find a journal article and you distill some of the statistics for them. So there's a couple different effects that I've used to test this as part of this exercise. But in this one, this is a study by Duesenberg and colleagues where they were looking at the effects of hydrocortisone on false memory recognition in men and women. And for the purposes of this activity, what we're looking at here is the percent of true recognition and the percent of false recognition on men and women. And so the authors drew this conclusion. So they said that women outperformed men for true recognition performance, and they present the t-test. There was no difference between men and women. There are false recognition performance. And so what you can do is, and what I've done with my students is try and get them to think a little bit more about, like, what does this result really mean? And do that from the perspective of power. So did these authors have the power to observe any of these effects, the difference in the true recognition or the difference in the false recognition? So because the authors presented the means and standard deviations for the different conditions, I was able to calculate the sample size and give that to my students. And so what that means is then we can go over to G-Power and we can calculate the post hoc power and the a priori power. So that's what we'll do next. So when you first launch G-Power, you get the default that comes up with t-test, and we go down and select a t-test for the difference between 2 independent means. And the first thing that I like to have students do is calculate the post hoc power based on the effect sizes and sample size observed. And so we can go down and select that here. And so we're going to do a two-tailed test. And in the article that we were looking at, the first effect for the difference between men and women in true recognition, that effect size was 0.63, and our sample sizes were 37 and 38. And so if we calculate power on this, we see that we get 0.77 if we were to round to 2 decimal places. So for the larger effect sizes on this sex difference that we're seeing, the study is not powered essentially to detect this effect. And then the other difference the other effect where they failed to see a difference between men and women in false recognition, the effect size for that was 0.25, and we can just change that parameter and have it calculate again. And here we see the power to detect this effect was just 0.19. And so essentially, after running the power analyses, then we can come back to these study results and really ask the students, like, what is your, confidence that these results, for example, would replicate? What is the likelihood that maybe we would fail to replicate these results? And we can also, from the a priori power analysis, start to get a sense of the sample size that we would really expect to see or need to see in some of these studies. And so an exercise like this does bring the students awareness to the importance of large sample sizes and a potential reason why we might fail to see replication when we don't have those large enough sample sizes. Okay, so Susan and I would just like to thank you, and we can take any questions that you have.